So we have started last time discussing an example of steady laminar flow of Newtonian incompressible liquid in a spherical tube. And that spherical tube is aligned with gravity fields. So I'm going to redraw things again. So this is what I call example 2. So again, steady state laminar flow. Fluid is Newtonian and incompressible. And I have a cylindrical tube. And we said this tube has length L, radius R, it's my gravity. So I'm going to work with cylindrical coordinate system. So my Z is basically pointing in the direction of gravity. It could point upwards as well. That kind of depends on your particular situation and how are you solving it, and basically results in one plus minus change in the final equation. And we have R in this direction, or in all of these directions, really. Okay. And another thing that I have is theta. Okay, so there's this theta direction that is tangential to whatever point I'm in. My theta direction points tangentially to the circle of the radius r, r being the distance to the origin. Okay? So my coordinate system is a little different from Cartesian in the sense that at every point I have slightly different direction of my coordinate vectors. They're still orthogonal to each other. Okay? So coordinate vector with respect to r, theta, and z, they're all always orthogonal to each other, but they're changing directions as I'm moving around in my coordinate system. Now, what we're doing here is we're applying a method or solution method to these problems called shell balances. So I need a shell. Shell is a specific volume or little control volume in my coordinate system. So in this coordinate system, this shell will be sort of like a little annulus. Okay? So when I draw that, I have something like this. I'm going to exaggerate it a little. My shell is bigger than my tube, but oh well, things are not to scale. Okay. So this thickness is in z direction, delta z. It's delta r thick in r direction. And I'm assuming, so basically I'm going from z to z plus delta z, and from r to r plus delta r in terms of radii. And I'm sampling all of thetas. So it doesn't matter how I slice this in theta, so I'm not going to have theta dependence of this solution. And I'm assuming that my Vz is a function only of r. So my boundary influences the flow quite a bit. It imposes that no slip on the boundary. And I have nothing else, no gradients in other directions that would cause a difference in other directions. So basically my r is my dominant direction I depend on, sort of concentrically going toward the middle. And in the middle, I expect the fastest flow. And on the sides, it's a 0. And the other two velocities in this coordinate system, this is cylindrical coordinate system, so now we're going to have Vr and V theta, okay? And both of those are 0 because there's no gradient moving the flow in those directions. if I had a porous boundary for some reason, okay, I would have a flow in R direction. So if you imagining a well bore, right, you're going in R direction, that's how you're injecting things. Question?
Vz of Z is constant, right?
Vz of?
Z.
So it doesn't depend on Z. So I expect at steady state a steady state profile to form. So wherever I am, I see the same velocity profile, however high I am. Right? Because gravity acts on all of it uniformly, right? Alrighty. So we have to go now balance my momentum, right? And by momentum, I always mean momentum in its entire glory. Okay, so it has all of the components in there. And you're going to recall, we call it phi. So in this case, most of the momentum I'm concerned with is in z direction, right? But velocity is in the z direction. So in order to get z velocity profile, I got to balance that momentum first. And we know that we have that phi ij, where that's the momentum in j direction, or j momentum transferred across my coordinate I plane, right? So basically what's going to be relevant here are phi zz, phi rz, and phi theta z, except that theta we're not going to really have because I have symmetricity in theta direction. So this is my actually vector phi z, right? That is basically z momentum stress tensor. And I know that my components of my stress tensor were which ones? Pressure times identity matrix plus viscous stress tensor plus rho VV, that is convective. So convection means I'm moving with velocity v, and what am I transferring? Momentum, okay, as I'm going along. I could transfer all kinds of things as I'm going along. Okay, so what is going to be my, so I'm going to have the balance of different momenta, and we know that we have to balance things that are coming in, okay? In our case, my in boundary, right, will be this top boundary at Z, okay? And my in boundary will also be this boundary in going into R direction, right? Where's my cup? Okay. So going into R direction, right? And going out this way. So where is going to, how am I going to look at phi zz? Where is it? That is z momentum that is transferred across which plane? The plane. So I'm going to have something like this, right? And it's coming in at z, and it's coming out at z plus delta z. Right? Now z momentum can get transferred across R plane as well, right? So it's the same type of momentum, it's just transferred in different directions. And that one is right here, right? Coming in and coming out on the other side, right? So I have phi RZ, and this is at R plus delta R, and this one is at delta R, at R, delta R. Where did I come up with that? So let's balance those. In order to figure out how much of this is actually coming into my little shell, I gotta multiply it by area because stress tensor by itself is per area, right? So to get the actual amount, it's phi z at z times, I'm going to denote that area as AZ. Minus, on the other side, what's coming out is phi zz at z plus delta z. And I could call it AZ plus delta Z, but it's really the same as AZ, okay? Well, in my cup, it's not the same because it's actually, my cup is a bad example. But if I had a proper cylinder, right? Those top surface and bottom surface. Like my cup has a little curving to it. And then plus, I have this phi RZ at R times delta R. And again, the reason I'm using this notation is because I don't want to write of R and Z. Z is kept constant in this particular case. Minus phi RZ at R plus delta R. And again, I'm calling this hatched area here, I'm calling AR on the inside of the volume. And on the outside, that area is slightly larger, right? Because it's a slightly larger radius, and it's R plus delta R. So I have balanced the momentum, all of it. And now I need to add something else. What is missing in this mix? Gravity. So body force, that is my external body force that kind of uniformly works on the entire volume. These are the things that are going through the boundaries in and out. Okay. So the only way to change something in a control volume is to act on that entire volume, right? And go in and out of the boundaries. That's your balance of anything right there. Okay. It could be mass balance, it could be, in this case, momentum balance. Now, momentum I can change by body force. Mass I cannot change by body force, but I could change it by reaction, for instance, right? So there's some external thing that can happen volumetrically in there, in which case, in this case, it's gravity. And then there's stuff going in and out of boundaries. That's essentially your balance laws for anything that you're balancing out there. And right now we're balancing momentum for another month or so, okay? So I have now plus body force, which is rho g, and the volume of my element is what? I defined everything I need to define that volume. Well, I'm just going to make it simple. AZ times what? Delta Z. Yeah? A little height of this one. And I'm going to get to computing AZ in a second. So this is my external body force. Cool. So let's actually now do this computation since you're so eager to do it. AZ. So my AZ is the area of this larger disk minus area of the smaller one, right? Yes?
Yes.
So R squared goes away. And we're going to do first simplification here. Delta R is going to be small, and it's going to be sent to 0 in a limit. So this is delta R squared. This is delta R. As delta R is getting smaller, this is the dominant term. The second order term is way smaller. Okay? So I can approximate it with 0. Again, because delta R is presumed small, and we're going to actually shrink it. So this is approximately 2p R delta R. And my AR is the area of this side, so it's basically this perimeter times delta Z. So it's 2RP delta R. And AR plus delta R, well, it's the same kind of thing, just done for R plus delta R. So it's 2R plus delta R, P delta R. Delta Z. I was just checking if you're awake. I need another sip of coffee, apparently. Though, no matter how much coffee, if I'm talking in parallel to writing, either talking is a little off or writing is a little off. I don't do things in parallel. All right. Everybody good? We're now going to put it in. And what I'm actually going to do, I'm going to divide this entire thing. Let's see. Let's do an obnoxious color, green. So this is my balance here. And I'm going to divide by the volume, this AZ delta Z. Which indeed is actually 2PR delta R. So when I do that, I'm going to immediately recognize, just to shorten my writing, okay? This is AZ, this is AZ. Okay. So there will be a difference here that is divided by delta Z. And it's actually negative phi ZZ at Z plus delta Z minus phi ZZ at Z divided by delta Z, which reminds me of that partial derivative big time. Okay. So, and then I'm going to have here it's going to be a little more hairy because AR and AR plus delta R differ. I'm going to be able to get the delta Z out, right? But then the rest is, so let's work that part out. And then dividing here by AZ plus delta Z, ZZ. Let's do that. I'm going to save this. Save and open a new one. Okay. And I'm going to get rid of my obnoxious green. Okay. So I'm going to have minus phi ZZ. And I'm going to shorten again this as evaluated at delta Z and Z plus delta Z. This is just like, this denotes difference. So this is phi ZZ evaluated at Z plus delta Z minus phi ZZ evaluated at delta Z. Same as sort of integration by parts. Plus, then I have phi RZ evaluated at R, and that AR is 2PR delta Z, minus phi RZ at R plus delta R, 2PR plus delta R delta Z. And that is divided by AZ times delta Z, so I'm going to actually write out what that is. And I have plus rho G is equal to 0. The greatest thing ever on this thing is you can erase. Okay, so now we have to actually look at this a little harder. I would like to recognize some partial derivative here, right? But I have these two things that are different. Well, they're different and they're not. Let's look at the pattern analysis, if you will. I have R plus delta R, and I have R plus delta R here. And I have R and R here. I can get rid of 2p, that doesn't bother me, okay? And I can also get rid of delta z. Yes. So when I look at my pattern analysis, okay, this is a function r evaluated at r plus delta r, okay? And this is a function r evaluated at r, right? And that's precisely where I'm evaluating phi rz and phi rz. So does everybody agree with me if I say that this is plus phi rz times r evaluated at, well, in this case, it's at r and r plus delta r. Yes? Because this is also a function of r and z. It's my phi rz multiplied by r, and in this case, I'm evaluating it at r plus delta r. This is one of those things that requires a step back. Okay, let's look at things from distance. And I'm just gonna do, to be closer to my derivative, I'm gonna put the minus here, and I'm gonna put this delta r here, and right? And then divided by delta r. I'm liking this much more, do you?
There is one more harmony.
Yes. And plus rho g is equal to 0. And now I'm going to take my limit as delta z goes to 0. Delta z and delta r. Okay. So this is my, should do my obnoxious green again, limit delta x, delta x. And then I somehow come up with x. I'm missing my Cartesian coordinate system. Okay. Then they go to 0. For color green, this is coming on screen like pretty well. Normally, this choice of green is horrible for screen, by the way. So if you're ever creating a plot that is going into a PowerPoint, do not use this green, which is often a default choice in a lot of plotting software. Do not use. Alright. So when I send this to limit, this is my partial derivative, right? When I send delta r to 0, that does nothing to this r, so this is simply 1, it remains 1 over r. But the rest is the derivative with respect to r of r phi rz. And, well, rho g is a constant. This r here and 1 over r here are a direct result of the fact that my area is changing with r. Okay? And you're going to have this in cylindrical coordinate system. And you have this equation. We did not have this type of 1 over y or x or a z or anything of that sort in a Cartesian coordinate system because all of my sides of all of my control volumes are always the same. Okay? The fact that my shell actually physically changes to a bigger shell as I'm moving out is basically reflected in this r and 1 over r. If we had a spherical coordinate system, you will get r squared in there because of that. Because the sphere is curving in 2 directions as opposed to only 1. Cylinder is curving only in 1 direction. In this direction, it remains straight. So when you see, we will kind of just use the formulas from the back of the appendix, right? Depending on which coordinate system you're in. And when you see this r and 1, like let it just click in your brain, that's that compensation for the area, okay? So that it kind of makes more sense and it's easier to handle, okay? All right, this is our equation, main differential equation that is valid at every internal point inside of my volume. And there's nothing in this equation that is for the Newtonian fluid yet. Okay, so this equation is valid for any fluid that I'm trying to balance in there. Devil is always in the details, so let's bring in the devil in there. So I know that my phi has those three components, and particularly phi zz. Let's change color. My phi zz is blue this morning. My phi zz, do I have a pressure component? Zz, I do. So it's pressure plus tau zz, and plus there's that rho vv at zz is evaluated as rho vz, so that's vz squared. Okay. My phi rz, and my phi rz is red this morning. Do I have pressure? No. So I have tau rz plus rho vzvr, and that's, yay, 0, because my VR is 0. So what I really have is just tau rz. Cool. All right, so z derivative of this is dp dz, d tau zz dz, and d dz of vz rho vz squared. Oops, square in the wrong spot. Minus 1 over r ddr of r tau rz and plus rho g is equal to 0. Everybody following with me still? Or did I lose you about 20 minutes ago? No? Okie dokie. Now my favorite part is killing terms. Pressure depends on Z, so I can't do that. We had that P0 and PL, right? Two different pressures. That's what's actually driving it. In addition to gravity, that's what's the driver for the flow. That's the gradient that is driving it. So, yeah, it depends on Z. Then I have tau ZZ. Tau ZZ in itself depends only on VZ, right? And this VZ, I'm looking for the partial derivative in Z direction of VZ, and that I don't have, so that I can kill. Again, because my VZ does not depend on Z. Same story here. So VZ is VZ of R, and that's going to kill both of these terms. So what I really have is this, and this term. And I'm going to just clean it up a little as 1 over R. The R tau RZ is equal to, and I'm going to have minus dp dz plus rho g. Everybody please check my pluses and minuses here. And this part here, I'm going to say, well, it's d dz of p, I'm going to remind myself, it's p of z, minus rho gz. Does everybody agree with this statement? I'm just going to shorten writing and call this capital P of Z, which is my generalized pressure. So basically I'm putting hydrostatic pressure inside of any other thermodynamic pressure gradient. possibly you already have, if you were working in the lab, it's not that you can separate gravity right? Easily. Gravity is always there. So if you're measuring these two pressures, you're already measuring it within, right? You just know that there is a rho GZ component inside of your pressure measurement. Is everybody following what I'm rambling here about? So this generalized pressure is already the boundary conditions you have from the lab, if you will. Okay? It's just in terms of solving things, because there are differences. There's a thermodynamic pressure that we are separating from the gravity component, because sometimes I'm ignoring gravity and I don't have that component. Right? So analytically, we like to separate the two. So I'm going to call that generalized pressure. Don't think about this formula in an absolute way. Whether it has a plus or minus here in rho GZ kind of depends on how I orient my coordinate system with respect to gravity. So in certain situations I might have, or rather if I oriented my Z in the other direction, I would have here plus rho GZ. So don't think about it in an absolute sense. So my generalized pressure is always P of Z minus rho GZ. It could be plus rho GZ. Okay. Rambling over, let's keep solving. Okay. So now I have to solve the equation, and I do have dependence on R and Z, or at least formally. So I have 1 over R partial R, or R tau RZ, is equal to minus dP dZ. And this, my pressure is function of Z. Tau RZ is a function of R because VZ is a function of R, right? And I only have, so I'm going to put R. So I'm going to observe here, this is a function of R. And this is a function of Z. And whenever I'm solving partial differential equations, that's something to look for and check whether you have anything of that sort present, because it's one of the methods for solving partial differential equations, which are hairy to solve. So the only function of R and a function of Z that are equal for all R and Z, this is valid for every R and Z. Valid at every point. The only function that satisfies that is a function that doesn't depend on R and Z. Okay? And that's a constant. Are we following the mathematical argument here? So it has to be constant. So my minus, and I can now switch to writing to direct derivatives, whether I write partial or regular derivative, doesn't matter. P is P of Z. Of Z is constant. No surprise there. We always kind of model pressure as a linear function of Z. So P is linear function of Z. So my dP dZ is the same as P evaluated of L minus P of 0 divided by entire distance L. And those are actually my boundary conditions, if you remember. So that's my PL was my boundary condition minus rho GL minus P0 minus rho G times 0 divided by L. In other words, I can solve this. I have this. I can just actually keep dp dz. I know what that constant is based on the boundary conditions. So this constant we know the constant from boundary conditions given at the beginning. I might have forgotten to write them today. I did last time. So I have pressure P0 and PL at my boundaries. So then let's solve for the left-hand side here. This we know. My 1 over R, VdR of outer RZ is equal to dp dz. I could just leave it as that because it's a constant I know, or I can just say, well, this is P0 minus dp dz, so it's P0 minus PL over L, and these are capital P's again, those generalized pressures. So my R tau RZ is integral of R times this, right? So P0 minus PL over L, that's my constant. Integral of R is R squared over 2. And plus some constant C1. And my tau RZ is then P0 minus PL over L. I'm dividing by R here, so it's R over 2 plus C1 over R. That's my solution for shear stress. This one? This? Oh, so yeah, so on my boundaries, I said that I have pressure P0 and PL here, given, right? So they were given. And then I have L, so then I know generalized pressure too, because that's just adding rho g L. Okay. So that I have PL, I know it, minus rho g L, I know all those three, minus P0, I know P0 divided by L. So that's my constant. So I could also in this formula just write minus dp dz. Like it's a constant that I know, it doesn't matter. Are we comfortable with all of these so far? Questions? This example you have to really be comfortable with. That's understatement of the year. Okay? This is the foundation of everything. All right, so I have my tau RZ, so I have computed my shear stress. I need obviously a boundary condition to figure it out fully. So I'm gonna look at, so this is my shear stress depends both on R and 1 over R, which is the interesting part because in my thin film example, I really had just difference on X, so it was sort of a linear function of X. Here I have a linear function of R, and then I have this 1 over R business. Now, since I'm in a tube, my radii go from 0 to R, capital R, right? So that means that if I had this C1 over R, it would blow up at 0. That's not physical. This is a mathematical solution that works in a generalized case, right? This mathematics doesn't know about any boundaries or anything just yet. I didn't introduce them other than in this boundary or knowing dp/dz, right? So this is more general than we actually need. In this case, when I have a geometry that has R is equal to 0 as part of it, I cannot have shear stress blow up. That's not physical, not in my laminar flow anyway. Okay? So basically my C1 has to be 0 simply because I have to have finite shear stress at that point. Now, which geometry that is in cylindrical coordinate system doesn't have r is equal to 0 within? Can I ask again? So which geometry in a cylindrical coordinate system does not have r is equal to 0 as part of it? Annulus, okay? In Wellbore, very important. If I'm flowing things in to go cement my well, right? I'm flowing in an annulus. Or I might have a tool in the middle. I'm flowing around it, okay? So there are geometries, so this is the most general case, that is where it's working for annulus as well. So in annulus, I cannot assume C1 is 0, because 0 is actually not part of my system. It doesn't bother me. Okay? So again, this is a mathematical solution that is more general. We're going to say, haha, r is equal to 0 has to have finite tau RZ, or shear stress. This is laminar flow. We're not modeling supernova explosions. So therefore, C1 has to be 0. So this disappears for cylinder, doesn't necessarily disappear for annulus. Okay? So this is for cylinder, not for annulus. So if your brain goes on automatic and simply cancels it and you're solving for annulus, you're in trouble. Okay? So I indeed actually have a linear relationship between my shear stress and radius. And I again have, so where's my maximum shear stress in absolute value?
Equals capital.
So at the boundary again, at the solid boundary, I'm maximizing shear stress. So just keep that physically in mind. Maximizing in terms of value. Plus or minus is something that kind of depends on how I define my coordinate system with respect to my geometry. So it's not all that important, okay? But in absolute value, I'm maximizing on the solid boundary. Okay. Like for instance, I could be flowing outside of this cylinder, and if I'm flowing outside of the cylinder, then I'm going to flip the sign of the shear stress in the same coordinate system, right? Whereas if I'm flowing on the inside, right? So again, plus minus is something that is coordinate system relative to my geometry. Physically, it's not all that important. Yes, it can bite me in my calculation, but physically, the meaning of plus minus is just kind of relative to my defined coordinate system. So I have, again, the same situation where I have a linear dependence of shear stress between, in this case, my coordinate r. It was coordinate x in the previous case. And I'm minimizing it at the middle of geometry in this case, and maximizing it in absolute value on the boundary. So it's maximized on r is equal to r, which is my solid boundary. And if I had an annulus and another solid boundary, right? Then I'm also going to have a local maximum on that boundary and local maximum on the other boundary. One of them will be positive, one of them will be negative. And I'm going to go through 0 somewhere in between. So it's kind of a physically much different situation. And that reflects in the flow pattern as well.
So in our annulus, we have 2 points of minimum shear stress.
Yes, one of them will be positive, one will be negative. But in absolute value, you have kind of local maxima on those boundaries. And 0 is somewhere in the middle, wherever you have the maximum velocity. So maximum velocity, minimum of shear stress in absolute value. Cool, let's now solve for that velocity that I keep talking about. Okay. So my tau RZ is P0 minus PL over L times R2. So what is my tau RZ? I don't have dVr dz. Now, one thing, in this coordinate system, this actually works, so tau RZ is kind of looking VR VZ, looking as the same as my Cartesian coordinate system. Don't ever assume that by default. Look it up. Okay, so different coordinate system could have slightly different. Okay, so go back in appendix. Somebody will tell me which appendix number you have shear stresses defined for Newtonian. I believe it's B, but I don't know. In the back, there's an appendix. So always verify in appendix the formula itself. And again, for the test, I'm going to give you a copy of important tables in appendix. So don't just assume that like a same formula works from Cartesian in cylindrical. Remember that 1 over r and times r? Okay, it could be different. So this, dVzdr, you mean my handwriting is bad? Really? It is. I'm not confused. dVzdr plus dVr dz. And especially deltas, rhos, like those things, I'm bad. I know. I have years of students complaining and how I write delta or rho. So rho, delta, that's all kind of some same squiggles in my world. All right. So back to, so this was just a side comment. Did I get the number in appendix?
B2. B1.
B1. All right. All right. So that's P0 minus PL over L R over 2. So my dV/dZr I can divide by minus mu. And then my Vz, so now I integrate. My Vz of r is minus 1 over mu L, P0 minus PL. And then when I integrate, I have 2 from here. And I integrate r, that's r squared over 2. I hope you're following my convoluted logic here. And I have another constant. Which boundary condition and am I going to apply for that? So my Vz of r is equal to, look at this timing, 0. And that's going to give me C2, which is the same as this, just with a capital R in there. And if you allow me, I'm just going to write down the final. For mu L. No slip. Slip. You can't read? By December, you will be a pro in reading my handwriting. And my last name says I'm already a pro. One of these days, I'm just going to cut part of my last name to be Dr. Pro. Professor Pro, Dr. Pro, all sounds really good. All right. So this is my famous parabolic profile. Okay. So basically, if I look at the cross section, what I'm going to see is that I'm going to have the largest velocity, and this is kind of curving. Okay. So I'm maximizing velocity in the middle, minimizing it on the solid boundary in absolute sense, and the opposite is true for my shear stress. All right. See you on Friday. One of these days, so focus a little on chapter 1, these definitions of phi, tau, who is positive, who is negative, in which geometry, how does it work. There will be a quiz on that, okay?